Now this is theorem number 6. According to this theorem, the perpendicular from the center of a circle to a chord bisects the chord, right? So what this theorem says? If suppose we have a circle, right? Let's draw a circle now. Draw a circle. This is a circle, okay? And the center of the circle is suppose O, right? Now, there is a chord, suppose. In the circle, there is a chord. This is a chord. You can draw this chord anywhere, right? So if this is a chord name is AB, right? Now, if we draw a perpendicular from the center of a circle to a chord, right? That means from the center, if we draw a perpendicular over this chord AB, right? Let's draw this. We'll draw perpendicular. Suppose this is a perpendicular. Okay. So this is the perpendicular we have drawn from the center on the chord, right? And suppose it touches the chord at a point L, right? Now, what it says that it bisects the chord, right? That means if you draw a perpendicular from the center of a circle to a chord, you can take any chord anywhere, right, in the circle, that always bisects the chord. This is the theorem. Is that clear? It bisects the chord, means it divides the chord into two equal half, right? That means AL, this portion is equal to this portion. AL is equal to BL, right? Okay, if we draw a perpendicular from the center of the circle to a chord, it will bisect the chord, right? So now what is given here? We will prove this now. So very first we will write down what is given here. Given a chord AB, this is a chord AB, as you can see here in the diagram. So this is given here that this is a chord of a circle. Circle is suppose C, O, comma R, right? C, O, comma R. O is the center, R is the radius. And we draw a perpendicular OL over OB, right? That means OL is perpendicular over AB. This is given, right? That there is a chord AB in a circle C, O, comma R, and OL. This line is perpendicular over AB, right? This is given to us. Now, what we have to prove? We have to prove that LA is equal to LB. That means this perpendicular is bisecting the chord, right? That means this length is equal to this length, right? AL is equal to BL or LA is equal to LB. This we have to prove here, okay? Now, what is the proof for this? We will do a construction here, right? What we will do? We will join OA and OB, right? So join OB and OB. OA and OB. Okay, we have joined OA and OB. Join OA and OB. Right? Now, by joining these 2 points, OA and OB, we are getting here two triangles. If you can see here, this one triangle, another triangle. Right? There are two triangles you can see, OLA and OLB, and both are right angle triangle. Yes or no? Because this is the perpendicular. So this is making a 90-degree angle here. Right? Perpendicular is always at an angle of 90 degree on that line, right? So it is making an angle of 90 degree both the sides. So these two triangle OLA and OLB are right angle triangle. So write down in the right triangles OLA and OLB, right? In these two right angle triangles, what we have? OA, this is equal to OB, yes or no? OA and OB are equal. Both are radius of the circle, right? So OA is equals to OB, both equal to R, the radius of the circle, right? Now OL, if you see this line, OL, this side is common to both the both the triangles. OL is equal to OL, right? So this is common. This is the common side, right? Okay, and this is a right angle triangle, okay, which is 90 degree, right? So we can say that these two triangles, OLA, triangle OLA, is congruent to triangle OLB. By which congruence criteria? By right angle hypotenuse side, RHS, congruence criteria. Okay, so we have proved that these two triangles are congruent using RHS criteria. These are right angle triangle, right? So one angle is the right angle. This is 90 degree. Okay. Hypotenuse, we have already shown that these are equal to R, right? And any of the side. So either OL, right? So here we have taken OL, which is common, right? So right angle, hypotenuse, side. So in this way, we have proved that by RHS, these two triangles are congruent to each other. Is that clear? So once we have proved that these are congruent triangles by RHS property, other corresponding parts of the triangle will also be equal, right? So AL, BL are the corresponding parts of these two congruent triangles, all right? They must be equal, isn't it? So right now, from this, we can say that hence LA is equals to LB. This is equal to this. Okay, so we have proved that L is equal to LB. Now, since L is equal to LB, that means this perpendicular bisects this chord into two equal half, right? So how we have proved this? We have proved the congruency of these two triangles here, right? Okay, and by this we have proved that both the sides, right, AL and LB, these two both parts of the chord are equal, and therefore, whenever we draw a perpendicular over a chord, right, the perpendicular over a chord, it always bisects the chord. Is that clear? So this is theorem number 6. Now let's see the next theorem, theorem number 7, which is the converse of the previous theorem of theorem 6. Okay. Now what it says that a line drawn through the center of a circle to bisect a chord is perpendicular to the chord, right? So this is the converse of the previous theorem. So here we have a chord in the circle, right? And now we are drawing a line from the center which bisecting the chord, and this line will always be perpendicular to the chord, right? That means let's draw a circle first, and let's see what is given here and what we have to prove. Suppose this is a circle, right? Center is O. Okay. Now let's draw a chord here. Suppose this is a chord. Now, according to this theorem, if we draw a line through the center of a circle to bisect a chord, that means we will draw a line here. Okay. Suppose we are drawing a line here, and this line from the center is bisecting the chord, right? We are drawing a bisector here. It is the bisector of the chord, right? Suppose the chord is AB, and this line is OM. Suppose, right? OM is a line which bisecting the chord AB, right? Now, what we have to prove? We have to prove that this OM is perpendicular to the chord, right? So this line segment is perpendicular to the chord, right? That means it is making 90-degree angle, right, with the chord. This we have to prove here. Okay, so write down what is given first. So write down given. What is given here? That M is the midpoint, right? Why? Because you already know that OM is bisecting AB, right? So M is the midpoint of chord AB, okay, of a circle. This is a circle C, O, comma R. Means O is the center, R is the radius. Now, what we have to prove? To prove that OM, this OM is making an angle of 90 degree. It is perpendicular, right? That means OM is perpendicular over AB. This we have to prove. Okay. Now again, we have to do some construction here. What is the construction we'll be doing here to do this? We will draw lines. Means we'll draw O, we will join O and A, and we'll join O and B. Right? We'll draw these two lines. Write down join OA and OB. Right? Now let's see how to prove this. Again, by joining these points, right, by drawing these lines OA and OB, you can see there are two triangles again here, right? Isn't it? OMA and OMB, right? So now, assuming in these two triangles, O in the triangle OMA and triangle OMB, right? So let's see what we have in these two triangles. In these two triangles, OA is equal to OB, right? This is same as earlier. OA is equal to OB. Both are radius, right? Both are the radius of the circle. OA is equal to OB. Both equal to R, that is the radius of the circle, right? Now OM, this line segment, this side of the triangle is common to both the triangles. It is common to OMA and OMB both, right? So we can write that OM is common here. OM is equal to OM. This is common, right? And the third thing, this line segment, right? The segments, the part of this chord MA and MB, these are also equal because it is already given here that M is the midpoint of the chord, right? We have drawn a bisector of the chord from the center O, right? So this OM is bisecting the chord. This is already given in the question, in the theorem, right? So that means MA is equal to MB. This is given here, right? So you can see that all the sides, all the corresponding sides of the triangles are equal. OA is equal to OB, OM is common, and OM or MA is equal to MB. Right? So all the three corresponding sides of the two triangles are congruent. They are same. That means both the triangles are congruent to each other. By which congruence criteria? By SSS, side, side, side. Right? So write down. Therefore, triangle OMA is congruent to triangle OMB by SSS congruence criteria. Right? So by SSS, side, side, side congruence criteria, we have proved that these two triangles are congruent to each other. Right? So since we have proved that these two triangles are congruent, right, the other corresponding parts of the triangle will also be equal. Is it clear? Therefore, we can say that angle OMA, angle OMA is equal to angle OMB. Right? This angle will be equal to this angle. These are the corresponding angles of the two triangles by CPCT, corresponding parts of congruent triangles, right? So these are two equal angles, but we have to prove that this angle is 90 degree, right? Okay. So as you can see, these two triangles, in these two triangles, these angles are the linear pair of angles, right? Because OAB is the chord, which is a straight line. Okay. Right. So AB is the chord, which is a straight line, right? So these two angles are making a linear pair whose sum is 180 degree, right? So can we write it like, write down, but angle OMA plus angle OMB is equal to 180 degree, right? These are linear pair of angles, right? This theorem we have already done in lines and angles, right? Okay. That means, and since they are equal, so can we say that OMA is equal to angle OMB is equal to 90 degree. Each one of them is 90 degree. So since these two angles are 90 degree, we can say that this line segment OM, this bisector OM, is perpendicular over the chord AB. Getting that? So therefore, hence OM is perpendicular over AB. So this we have proved that a line which is drawn from the center of the circle to bisect the chord is always perpendicular to the chord. So this theorem is exactly the converse of the previous theorem, right? What was the previous theorem? That the perpendicular from the center of a circle to a chord bisect the chord, right? And if we talk it on in the other way, that if we draw a line, right, from the center of the circle which is bisecting the chord will always be the perpendicular to the chord, right? So these two theorems, right, theorem 6 and 7, 7 is the converse of the theorem 6, right? So both are same thing, just that we have proved that these theorems in both the ways. So I hope you have understood what we have done today. Yes or no? Now look at this next theorem, theorem number 8. What it says that equal chords of a circle are equidistant from the center. Okay, so this is an important theorem, right? Which generally comes, and questions are also there on the basis of this theorem, right? So what is the meaning of this? Equal chords of a circle. That means if you have a circle, suppose draw a circle, Suppose there's a circle. Okay. Now in the circle, we have two chords which are equal in length, right? Equal chord means which are equal in length. Suppose there is one chord, this, another is this, right? Okay. So suppose this is AB and this is CD. These are the two chords of the circle, right? Center of the circle is O. Okay. So circle is CO comma R. And in the circle, we have two chords AB and CD, which are equal. It is already given that these are equal chords. Now, these equal chords of the circle are equidistant. What does it mean? That means from the center, they are equidistant, right? That means what? If this is given here, what is given here? A circle CO comma R, right? In which chord AB is equal to chord CD. These chords are equal in length, right? And equidistant means what we have to prove that if we draw a perpendicular, right, from here to here, okay, from the center to the chords, like this and this, right? Okay. Okay. So this is M suppose, and this is L suppose, right? Okay. So distance between the center and the chord is the shortest distance, right? So OL is the shortest distance, OM is the shortest distance. So here OL is perpendicular over AB, right? Okay. And OM is perpendicular over CD, right? So this is perpendicular over AB, OL is perpendicular over AB, and OM is perpendicular over CD, right? Okay, so these are the two perpendiculars, right? Now, what we have to prove? We have to prove that these OL and OB, these perpendiculars, are equal, right? So OL and OM, these are equal. If you prove this, then only you will be able to prove that they are equidistant from the center O, right? So what you have to prove that if there are two chords which are equal in length in the circle, then they will be at the equidistant from the center, right? That means if we draw a perpendicular from the point O to both the chords, then these two perpendicular are equal to each other, right? In length, right? Okay, that means they are equidistant from the center. So here we have to prove that OL and OM are equal, right? Now, again, we will do some construction here to prove this. And the construction is that we will join OA and OC. Okay, we will join OA and OC. So let's join it. OA and OC. Okay, so this we have joined. Now, how to prove this? We know that perpendicular from the center of the circle, from a circle of a circle to a chord, always bisect the chord. This we have already proved in the previous theorem, right? That is our previous theorem, that whenever we draw a perpendicular, right, from the center, that like here we are doing this, right? So we are drawing this perpendicular from the center. This is perpendicular from the center to the chord AB. Then this will be always bisecting the chord, right? Similarly here, OM is the perpendicular over CD. So this OM will bisect the chord CD, right? So this is according to the theorem which we have just learned in the previous section, right? Okay. So what we will do to write down as the perpendicular from the center of a circle to a chord bisects the chord, right? That means what? If OL is bisecting AB, that means what? It means that AL is equal to half of AB, right? Okay. And CM will be equal to half of CD, right? Because OL is bisecting this chord. So AL, this part will be half of AB. And similarly, CM will be the half of the chord CD, right? Because these perpendiculars are bisecting the chords, right? According to the theorem. Now, since they are bisecting, right, can we say that? And AB is already given to CD, right? AB is equal to CD. This is already given here. isn't it? So these two chords are equal in length, right? Okay, that means, so write down, since AB is equal to CD, right? Can we say that half of AB will also be equal to half of CD, right? If the two chords are equal, then their half will also be equal, isn't it? Right? By the axiom, Euclid's axiom, right? So half of AB is what? AL. And what is half of CD? This is CM, right? So write down, half of AB is AL and half of CD is CM. Okay. So what we have proved, that AL is equal to CM, right? Means this part of the line segment is equal to this part. AL is equal to CM. This we have proved. Now, from this, what we will do? Now we will consider the triangles. Now, in right angle triangle, OLA and OMC, right? So if you see by construction, we have got these two triangles, triangle 1 and triangle 2, right? Both are right angle triangle because OL is perpendicular over AB and OM is perpendicular over CD, making 90-degree angle. So these two triangles are right angle triangle, right? So now in these two right angle triangle, let's see what we have. So AL is equal to CM, right? This is suppose equation number 1. Okay, this we have proved in the above section, right? That AL is equal to CM from equation 1, right? OA is equal to OC. So look at here. OA is equal to OC. They will be equal. Why? Because both are the radius of the circle. OA and OC are the radius. These are the radii of the circle, and they will be equal. Okay, each equal to radius r, right? Okay, and this is a right angle triangle, so 90-degree, 90-degree. We already have this, right? So can we say that triangle OLA is congruent to triangle OMC, right? These two right angle triangles are congruent by which criteria? By right angle hypotenuse side criteria, right? So by this congruence criteria, by RHS congruence criteria, we have proved that these two triangles are congruent to each other. Everybody understood till here? Yes or no? Now, since we have proved that these two triangles are congruent, now by CPCT, corresponding part of congruent triangles, can we say that OL is also equal to OM, right? Okay, because we have already proved that these two triangles are congruent to each other by RHS criteria. So by corresponding parts will also be equal now. So OL, this line segment, this side of the triangle will be equal to the corresponding side OM, right? And this was the one which we have to prove, isn't it? So write down. So therefore, we can say that OL is equal to OM by CPCT, corresponding parts of congruent triangles, right? Hence, AB and CD are equidistant from center O. Is that clear? So since OL and OM are equal in length, that means these two chords AB and CD are equidistant from the center, because we have proved that these shortest distance, right, are same. OL and OM are same. That means AB and CD, right, these are equidistant from the center O, right? So this was the theorem 8, that equal chords of the circle are equidistant from the center, which we have proved. So I hope everybody understood. Yes or no?